All right. So before the quiz, we had been looking at kinematics, of course. We looked at basically a few types of quantities that we considered: the map, the deformation map, which is what describes how a body goes from undeformed to a deformed configuration. Based on the deformation map phi, we got the deformation tensor, deformation gradient f. From f we got c, from c we got e, and we were trying to interpret what are the physical meanings of all of these quantities. So I think in the last lecture before the quiz, we looked at the physical significance of the components of C and E. So anybody remember, if I have a C tensor, something like this, what do the diagonal entries of C, what do they represent? Say it again. Squares of stretches, yes. So a diagonal entry like C11 or C22 or C33 would be nothing but E1 dot with C acting on E1, right? And that would pick out the C11 entry, and that's the normal square of the normal stretch in the 1,1 direction, similarly 2,2 and 3,3. We saw that the off-diagonal components represent uh, are proportional to the shear angle beta. For example, in this case, we looked at that, and then just about when we where we closed last time was on this idea of principal directions for deformation tensors and strain tensors. So the idea was that given any undeformed body and the corresponding deformed configuration, then go to any point in the undeformed and the corresponding point in the deformed configuration. You will have the set of undeformed tangent vectors in the undeformed body, the corresponding blue ellipsoid, which is the set of deformed tangent vectors in the deformed body. Now, since this is going to be an ellipsoid, this means that in certain directions, the stretch or the strain would be a maximum or a minimum quantity. And we said that to find which directions those maximum or minimum occurs, we will set up an optimization problem where we will say that the function that we'll try to maximize or minimize will be the square of the stretch, subject to the constraint that n, the direction, has to be a unit vector. So n dot n minus 1, that's a unit vector. So that's an optimization problem as we write it out here. Now, to find the maximum or minimum of any function, we take the derivative of that function with respect to its dependent variables and set them equal to 0. Right? If you want to maximize or minimize a function f, is going to be not sure. Okay, I'll have to fix this for next time, but let's maybe bear with it today. So the maximum or minimum would occur at a point in a direction n where this function, this modified function, with respect derivative of that with respect to n goes to 0, or derivative of that with respect to mu. Mu is a multiplier, an arbitrary multiplier, which is called a Lagrange multiplier, where derivative of that L with respect to mu also goes to 0. So all we have done is, this is a function of two variables. I'm setting its partial derivatives with respect to its independent variables to be 0, and that either maximizes or minimizes that function. We found that led to this equation Cn is equal to mu n, which was nothing but the eigenvalue problem back when we were looking at tensors. It says that the tensor C acting on the vector n has the same effect as stretching the vector n by an amount mu. That's what a tensor does in one of its eigendirections. It does not change the direction of that n, it only stretches or contracts it by some amount, mu. So So we also showed that that two eigenvectors that are not the same, like ni and nj. If we pick two of the eigenvectors ni and nj, if they are not the same, then the angle between them would still be pi over 2, and that means that between two eigenvectors there is no shearing, right? And this is important because of what we discussed in this example. Anybody remember what we called this deformation profile? Simple extension, actually. Simple shear is this one, where we take the top face and we just kind of shear it. But this deformation profile is simple extension. All we are doing is x2 is equal to z2, x3 is equal to z3, and x1 is equal to alpha times z1. So it's a simple extension in one direction. Even for this simple extension problem, we saw that any vector that is not along the vertical or horizontal direction, you remember we stretched this thing and played with it a little bit. So initially it was like this. This was the black configuration. And as I stretch, except for the vertical and the horizontal vectors which do not change direction, each and every other vector in this profile changes the direction a little bit, right? So that means that even for something as simple as simple extension, you are going to have shearing in infinitely many directions except only the two eigendirections, which is going to be true in general as well, which is what we are saying here, that if you have two eigenvectors that are not the same, then the shear between them is going to be 0. And finally, if you use the same logic to try to maximize or minimize the strains or the directions of the strains, you get the corresponding eigenvalue problem for the strain tensor. And you can show very easily that the eigenvalues of the strain tensor are nothing but half times mu minus 1 eigenvalues of the deformation tensor. You remember E is equal to half of C minus I. So gamma, the eigenvalue of E, is equal to half times mu, the eigenvalue of C, minus 1, which is the eigenvalue of I, right? So it's a nice way to find eigenvalues and eigenvectors of C and E. If you know the eigenvectors and eigenvalues of one, you easily know the eigenvalues of the other, and the eigenvectors remain the same. So, so that's kind of a interesting note here. All right. Now let's take a look at something that will help us interpret what the deformation gradient does to an undeformed set of tangent vectors in a very physical kind of a way. So you remember we said that if we have a body, it's deforming to this black body, deforming to this blue body, go to any point in the undeformed body, and in the neighborhood of that point, I will have this infinitely many set of undeformed tangent vectors that will get mapped to the corresponding ellipsoid of our corresponding deformed tangent vectors. Now, we know that it is the F tensor that relates dz tangent vectors undeformed to dx tangent vectors that are deformed. So F does that. Now, another way to interpret this process of deformation, that I'm taking this ball, this sphere of arbitrary black vectors, and I could reach this final deformed configuration in one of two ways. Or one, by decomposing F into two tensors. One, a pure rotation tensor. So let me write that here. R here is a pure rotation or orthogonal. Orthogonal tensor. So you remember maybe back when you were doing homework 2 that we had a tensor Q. a tensor Q that used to take tensor vectors E1, E2, E3 to the corresponding G1, G2, G3. That was a rigid body rotation of the basis vectors E1, E2, E3 to G1, G2, G3. That Q was an orthogonal matrix or orthogonal tensor, because Q transpose Q was equal to identity and Q times Q transpose was equal to identity. This R is also an orthogonal tensor. All that it does is it takes the undeformed, so I'll come to that. It takes any set of vectors and just does a rigid body rotation of that. On the other hand, this U is uh, is a symmetric and is a symmetric deformation tensor. So this U is a symmetric tensor, and that gives me a unique decomposition of F into two tensors R and U, and the way that it would act on an undeformed tensor dz when F acts on this to give me dx, the way I would write that would be R times U is a tensor dz, and first U will act upon dz. U acts upon dz to do some stretching. Since it's a symmetric tensor, it has in general, three eigenvalues and eigendirections. So let's say I pick out the eigendirections of U tensor, which is n1, n2, n3. In those particular directions, the effect of U tensor is only to do stretching. So it stretches n1 to un1, n2 to un2, and un3 correspondingly. It does not do any rotation of those three vectors, but every other vector goes from here to this configuration. Every other vector does have some rotation. Following that, since U times dz is also a vector, R tensor is going to act on that black ellipsoid, which is a rigid body rotation to the final configuration. So it still takes the original undeformed tangent vectors to the final deformed tangent vectors, but it's a two-step process. One is a pure stretching in the eigendirections, and followed by a rigid body rotation through R. So U1 goes to F times N1, and similarly for N2 and N3. And the other rotation, other way to interpret F is through V and R, which again, if we interpret that as V tensor, R tensor, dz vector, and there's a vector here, so dz is a vector. R times dz acts first on dz, which means undeformed tangent vectors are just rigidly rotated to their correct final directions. Then following that, rotated tangent vectors are stretched by a V tensor, which is symmetric. So I'll write that again. V here is symmetric. R here is orthogonal rotation tensor. And this R is the exact same R tensor in the RU decomposition. So F is equal to RU or VR, that R is the same R. Okay. So these are two alternative ways of interpreting F, which help us quite a bit, because F directly does not capture the strain. It also captures some rigid body rotation. R here is the rigid body rotation that we want to get rid of if we want to calculate strains, right? So that's why this way of interpreting the deformation tensor F turns out to be useful. Go ahead, you get a question?
We say that R is a pure rotation tensor.
That's right.
But V and
U,
can we call them as pure stretching tensors?
So they are indeed stretch tensors, but so what they do is, so for example, U will stretch N1 to UN1, N2 to UN2, N3 to UN3. Now these three are simple extension problems in or simple extensions in three different directions. So let me ask you this: if I have a simple extension in one direction, simple extension in another direction, simple extension in the third direction, can I say that it's a simple extension in any other arbitrary direction? No, right? So yes, in that sense, U and V both are pure stretch tensors only for the eigendirections. But for any other direction, it will cause some stretching and rotation in general. Okay. All right. So this allows us to rewrite essentially the definitions of strain using using this concept of polar decomposition. This is, by the way, this decomposition of F is called the polar decomposition. So one way to interpret this again is, you remember the left hand rotation or the left deformation tensor B that we came up with, we defined as F times F transpose. This was way back, probably somewhere here, right? So if the effect of F is only to do a pure rotation, then we found two definitions of strain which were proportional to C minus I or I minus B inverse. This B inverse is what I'm talking about. B is F times F transpose. Substitute for F, F transpose is VR transpose. If I rearrange that, I get R transpose R is identity, and we find that B tensor is equal to V times V transpose. Since V is symmetric, V transpose is equal to V, and we get is equal to V times V or V square. So the way to find these two tensors R and U, if you are given F, or if you are given the map, you calculate F. From F, if you have to find out B and or U and V tensors and R tensor, one way to do that is to first find B. B would be F transpose F. Once you find B, you can find V. Can you take a guess how? How would you find V, which is equal to, or V square is equal to B? How would you do that? Right, so you would indeed use the spectral decomposition of B now. Spectral decomposition was finding the eigenvalues and eigenvectors of B. And eigenvalues of B would be lambda square. So when you square a tensor, if I have a tensor T, then I can construct a tensor T square, which is just T acting on T itself. It's a composition of two tensors. The eigendirections do not change, right? And the eigenvalues just get squared. Any idea why? Why do eigenvalues get squared when I do tensor times a tensor? Let's see. Special cases, maybe. Right. In the basis of its own eigenvectors, a tensor is just has the diagonal components, right? So if I do T times T, what do I get? Just the squares of the diagonals, which means that eigenvalues of eigenvalues of V squared would just be the square of the eigenvalues of V. So we can write this as sum of I going from 1 to 3 of lambda I times the same eigenvectors mi dyad mi, and the same thing on the right hand side deformation as well. C is equal to F transpose F. F is equal to RU transpose, so RU, and taking the transpose of that, I get U transpose, R transpose, R and U. In the middle out here, that goes to identity. Therefore, U, that C is equal to U transpose, which is same as U, and another u there. So we get c is equal to u square and b is equal to v square, which also means that we can find u from c just by doing the same process with the spectral decomposition, I going from 1 to 3, lambda I, and ni dyad ni. What are these ni and mi vectors? Let's try to understand that. These ni and mi vectors are vectors, unit vectors in the deformed and the undeformed configurations. N1, N2, N3 are the unit vectors, unit tangent vectors in the undeformed configuration that are stretched by u into un1, un2, un3. So n1, n2, n3 are the eigenvectors of u. Okay, and after rotation they go to their final correct deformed orientations. On the other hand, R tensor just takes n1, n2, n3 and does a rigid body rotation of them to m1, m2 and m3, which are nothing but R acting on n1, n2, n3. Okay, so R does a rigid body rotation of the same three eigenvectors into m1, m2, m3, and now V acts on them to stretch them to fn1, fn2, and fn3. The magnitude of m1, m2, m3, and n1, n2, n3, they are all unit vectors. Okay. All right. So with all of that, finally we have devised a way to find V and U. So if I have the map phi, I can find f. From f, I can find c. From c, I can find u. From f I can also find b, which would be ff transpose. From b, I can find v, like this. And finally, we have to find r. How do we find r? Yeah, we can just use the polar decomposition right here. F is equal to vr. So if I pre-multiply by v inverse, then what we get is v inverse f here, and on the right hand side, if f is equal to ru. So if I post multiply by u inverse, then I get f times u inverse, and that would be the way to find R and U decomposition tensors at a point if you know the map. Okay. All right. So this is a useful way to interpret F, the effect of F tensor on a undeformed to deformed, that it causes both stretching and rotation, but they can be decomposed separate of each other. And let's take a look at this example of simple shear. I think I probably have a MATLAB code to go along with this. Let me open that in the meanwhile. So in this example, this is the same simple shear example. We are going to try to find all of these quantities. And rather than doing all these computations by hand, we are going to use MATLAB to do that. So phi for this is z1 plus 0.2 z2. Unlike your quiz problem where this factor 0.2 was not there, factor was 1. So if you calculate f, you get this as the tensor. For c, you would be f transpose f. You get this as the matrix. And I'll run you through this computation of how you can use MATLAB to find out all these different tensors and the eigendirections and so on. Let me open up that code somewhere, polar decomposition, right? Okay, let's keep it here. So you can verify, maybe what I'll do is I'll put a breakpoint here, and then I'll run this problem so that we can see one at a time what the output is. That's the F tensor, that's what I've input here. C is equal to F transpose F, so that computes C. B is equal to FF transpose, so that immediately computes B tensor. Now I'm going to find eigenvalues and eigenvectors of C using n times D. So let's do that. we need the eigenvalues and eigenvectors of C to find its spectral decomposition, right? So n is these three vectors, the column vectors out here. These are the three n1, n2, n3 directions for the deformation. So let me go back and mark those. It's the same deformation, same vectors here. This is n1, this is n2, this is n3. And from the previous page on the handout, you remember we said that these are the directions in the undeformed configuration, the directions that when the U tensor acts, it does not change those directions. It just stretches them by some amount. By what amount does it stretch? It stretches them by 0.819, 1, and 1.22. So this is lambda 1, lambda 2, lambda 3. Actually squares of those, because this is the eigenvalues of C. So when I compute the actual stretches, which would be just square root of the D, which is the eigenvalues. So square root of those diagonal entries is given by this. So these are nothing but lambda 1, lambda 2, and lambda 3. So what we have done from the previous page is we've computed these n directions. We computed lambda squares. We took the square root, and now we have lambda 1, lambda 2, lambda 3. We have n1, n2, n3. So we should be able to construct the U tensor now. Okay? To construct the U tensor, what we'll do is we'll first verify that that these directions n1, n2, n3, that these directions are orthogonal. Can you think of a good way to check whether these directions are orthogonal, meaning perpendicular to each other? Okay, yeah, so we could do n1 dot with n2, n2, n1 dot with n3, and so on. And in matrices, it would be as simple as doing this n matrix times its self transpose, or n transpose times n. So first I'll do n times n transpose, you get identity, which immediately means those three vectors are orthogonal. And no surprise, the next one, n transpose n, is also identity. And finally, I'll also do the eigenvalues of B, which gives me eigenvectors m. Now these m are not in the same direction as n1, n2, n3, right? These are in the rotated directions. You remember n1, n2, n3 get acted upon by R to give me m1, m2, m3. Those are these m1, m2, m3s that we have just found. So let me see. I don't have that in my handout here, but this code is also posted on Blackboard. You can check it out by running it. And same thing for m transpose, m. Both are identities. No surprise there. And now let's construct the U tensor. So to do that, I will take n acting on L. Okay. N acting on L, and then times n inverse, which is basically going to be n transpose. So this n matrix acting on this L matrix, hopefully you can see that the effect of that is going to be lambda 1 times n1 plus, or in the second column, lambda 2 times n2, and third column, lambda 3 times n3. If I post multiply with n inverse, what I'm doing really is, since L is diagonal, then I'm taking the outer product of n1, n2, n3 with n1, n2, n3. And that is exactly what the U tensor is. That's what the spectral decomposition is. So if you do that, we get this is U acting only NL, and then in the next step I have UL n times L times n inverse, which is equal to n transpose. So the last two outputs that we get here are exactly the same. These are the U tensors that are obtained by MATLAB. And similarly, you can find V tensors. Once you have V tensors, you can find R tensor by F times U inverse or by V inverse times F. And those are all kind of written out here, so I'll let it run out. That's R, and you can verify that R is also an identity tensor. So take a look at this code. I went through it sort of quickly. I don't, but essentially what we are doing is calculating the polar decomposition of this F tensor field using the C and the B tensor fields. We found eigenvalues and eigenvectors of those, took the square root, and then just did the spectral decomposition of N for U and V. Okay, and of course, this can be a lengthy calculation for something that is not as easy as this. But at least conceptually, what you should understand is how you could calculate that, how you could calculate any of these tensors. If I give you an F tensor or if I give you a C tensor, how to calculate R, U, and V from them. Okay. Any questions on this? So it's okay. It's a lot of math, but there's a lot of physical interpretation along with to go with it, and I feel it's more important to understand the physical interpretation, and then the math will automatically come out of itself. So looks like we're out of time. Next time, which will be online, I'll discuss this pseudo-spectral decomposition, and hopefully we'll get to things like compatibility and changes in area and volumes. All right. So I'll talk to you on Friday online, and then following Wednesday after the October break will also be online. Okay, question?
Will we have a review session?
No, unfortunately not, because I'm traveling, so I won't be available for the review session this week. But next Friday, yes, we'll have a review session as usual.